Um, okay, so today we'll go through the fifth week for the course. Today's live session is going to be a little bit different. Rest of the days we like first the lectures, then some questions. Since today is more based on modeling and uh, ODEs and stuff, so it is not always possible to solve ODEs and all in a live session, and anyway we'll do it in MATLAB. So instead, what I've done is I've included some real-world examples of modeling and how you can go about them, and we'll discuss those. And at the end, I think we have one or two questions. So
Okay, sure.
anyway, we'll start. Let's see. Yeah, it's recording. So just to start, we'll talk a little bit about modeling in systems biology context. So this figure shows kind of the various steps involved in modeling, and obviously you basically start with a question. So the most important thing of your model is to what questions does it answer. So just a second. Yeah. Okay. So yeah. So firstly, yeah, what kind of questions you are trying to answer, and what kind of prior knowledge you have about the components of, say, you are trying to answer how a signaling pathway is working, or how a particular element of the signaling pathway is mutated, how it will work, how your phenotype can change, how your various uh, pathway mechanisms can change. So these kind of questions you're trying to answer through the help of modeling, and you need for your model to set up, you need prior information about the components, interaction, and the pathways or networks, whatever you are dealing with, and then you specify a pathway or a network topology, and you develop system of coupled ordinary differential equations from that network or from that pathways. We'll look into more detail about how we can develop these kind of ODs. And then after that, you need to parameterize the equations with initial concentrations and chemical reaction rates. So basically, your parameters will mainly be your reaction rates and your initial and final conditions of those differential equations that you make. Those will tell you about the initial concentrations basically, and then you use solving techniques, and you see what kind of predictions you're getting, and then you kind of check for how much error, how much deviation your error is showing with respect to the original kind of state that you are observing in a biological system. And then you do kind of parameter sensitivity analysis, so changing of the parameters slightly a little bit here and there to see how your model is changing with that. And you need to identify a set of parameter sets that match the experimental input output relationships. And then kind of this is a feedback loop, then you like kind of change the parameters according to your results and kind of according to your hypothesis, and then you do the simulation again. So this is kind of feedback loop that you go on doing with changing the parameters a little bit every time, and see if these simulations match your experiments. So if that is, see, like when you are trying to model this kind of systems, like you generally have any one hypothesis about the system, and that you are using it to model the whole system, and there are also factors that you already know that this is going to happen. So if that kind of the truth set is coming out of your model, say a particular interaction basically say happens in a system, and if your model's result are predicting that that interaction is occurring, then you can say it is matching the biological system, and your hypothesis is kind of true, and you can do these simulations to understand the network or the model or the pathway or whatever you're dealing with further. So this is kind of an overview, and in addition to these steps, you have to be careful that your models are based on chemical kinetics that conform to microscopic reversibility principles. And once topology and parameters for initial conditions are set without bias, that is, you have a prior expectations for this kind of systems behavior, the kind of behavior I was talking about, say two molecules are known to interact in a biological system. That kind of parameters, you can set the parameters according to that with the help of those kind of prior expectations, and simulations should be done without altering these conditions, as in like those inherent biologically true phenomena should be upheld in your model. So, and your parameter variation should be systematic, unbiased, and as comprehensive as possible. And the topology should be altered on the basis of biological knowledge only. And when simulation outputs do not match experimental observations for input output, and then you are changing, they will change your basically topology, and that should be based on fully biological knowledge only, knowledge of the system you are working, and then ultimately you match then ultimately you iterate over this process by changing the parameters and seeing how your system is how your model is responding, and if it is going closer and closer to your to a model biological system, or is it moving away from it. So yeah, this is kind of an overview, and we'll basically talk today about all these parts. So first we'll start with how do we get these ODs. Next we'll go into how do we basically solve these ODs. So in our case, in biological systems, we have very complex basically systems like pathways or networks. So we usually model these using ODEs, and as you know, ODEs, when you have a large number of ODEs, it is not possible to get analytical solutions for them. So, and also like only 1% of those ODEs are having analytical solutions. Many of them won't have. So the idea would be to solve them numerically. I'll not go into much details about how we solve them numerically. I've described a method called Euler method, but there are other methods as well, like Rangi-Gupta, and there are Taylor series methods as well, where you can expand the ODE and solve it. But yeah, that is the idea. We'll use numerical methods to solve these kind of equations. There are, I think, MATLAB sessions in the original course on how to solve those. We'll not go into them, but I'll just give you an overview over them. And after that, we'll see how we can do parameter estimation from these results, and how we can improve and fine tune these parameters, and ultimately how all these can come into and help you gain biological insight from a system of these equations, and we'll see a couple of examples from them. So okay, moving on. So first thing is how do we basically write ODs in case of biological systems. So say for example, x is given as a concentration of a substrate of a compound X, which can be an mRNA or a protein or a small molecule metabolite, can be anything. And at time t plus delta t, where delta t is very small, you can expand this into a Taylor series kind of. X of t into delta t can be expanded as approximately x of t plus kx into delta t. This is kind of the basically the different this is how differential equations or differentiation works basically. So and when you take delta t limit delta t tends to 0, you get basically dx dt. So here the function, yeah, someone saying something. Yeah. So basically, if your concentration is varying linearly, in this case as kx, this is basically first order linear autonomous ordinary differential equation. This is explaining that the rate of change of x over time is proportional to x itself. And here it involves two different quantities, where x is the state variable and k is the parameter. So this is the parameter we are interested in, and this parameter basically it does not describe any elementary component of the process, or as in it does not describe any kind of interaction or anything of that sort. It generally describes the reaction rate. So for in our cases, most of the times the parameters will describe the reaction rates, and we'll have some assumptions about those reaction rates, as in how it'll like go into steady state and all, etc., etc. We'll come to that, and basically K will tell you how the concentration of X varies with time. So dependent on K, if K is positive or negative, you'll attain a steady state in that particular way. Okay. So how do we solve this ODE? This is a very simple ODE, dxdt equal to kx. So you can just simply separate the variable. I'm sorry, I've missed basically divided by here. So it will be basically dx by x equal to kdt, and then you do simple integration on both sides, you get a logarithmic equation. So log of xt equals to log of x naught. X naught will be an initial condition, and plus kt. And if you take an exponent to this, it will look like something like this, basically uh, xt equal to x naught e to the power kt. This is a very fairly simple first order first order chemical kinetic equation that we all have seen previously. I think, yeah, this is basically a first order kinetic reaction. So this is very easy to kind of this kind of equations are very easy to solve. You can just simply separate the variables. So x on one side, t on one side, and take a simple integration will give you the equation. But in most of the cases, this will not be the case, as we'll see moving forward. So this basically this dx dt equal to kx. This is known as Malta's law. I'll not go into the details because it's kind of flawed. We'll not discuss Malta's law in detail, but I just want to give you an idea about how these kind of equations work. So basically, how does the whole equation depend on k? So if k is greater than zero, it will show an exponential growth, and if k is less than zero, it will show exponential decay. So kind of k determines how the value of k, if positive or negative, determine how it is going to reach a stable state. We'll see that later, how k is involved in determining that. But basically, yeah, this is the case. If k is greater than zero, you'll see a growth exponentially, and if it is less than zero, you'll see a decay. Now, how do you characterize steady state in these kind of ordinary differential equations? So, what does steady state determine? So, it determines a long-term behavior. So, basically, what happens if x reaches at what happens to x if t equal to infinity? At a very large amount, after a very large amount of time, what is the state of x? This is what steady state determines. So, uh, if one is lucky, it coincides with the steady state of solution of the ODE. That is the steady state values that is given as XSS, for which dx is equal to zero. So basically, uh, there's a little bit of difference between the steady state of basically a system and a steady state of a equation. So, but in our case, we'll generally assume the steady state of the ODE is basically determining the steady state of the equation, of the system. But in some cases, it actually isn't, because there are other equations and other constraints involved in those things. But since this is a fairly simple example that we are looking at, this is what we assume, that the steady state of a system is described when dxdt is basically zero. There is no change in the concentration of x, and basically the rate does not change. And here it says the OD stays there forever, and steady state excess is said to be stable when changing the initial conditions. The steady state remains the same. So I hope you remember in the first class we talked about stable and unstable steady state. So if you have a stable steady state, if you pull it a little bit out of the steady state, it'll go back to that state. But if I have an unstable steady state, there you just if you try to pull it out, it will not move back to the state spontaneously. So uh, there can be two kind of steady states, stable and unstable. At both of those points, it's basically dxdt equal to zero, but it's kind of finding the maxima and the minima. So where if the double derivative is negative, it's kind of giving you a stable steady state. It's kind of a minima. So you want if you imagine a curve, so your minima will be a stable steady state, right? So it will, if you pull something out of the minima, it will come back. You can like imagine a U. So at the bottom point of the U is the stable steady state. If you pull the element out of the state, it will come back to a state. But if you consider a maxima, it will be kind of an opposite U. So it will be like this. And if you put if your element is in that state, it's an unstable steady state, because if you push or pull the element a little bit, it will not go back there spontaneously. So that is the idea we employ while studying and solving these kind of ODs. Okay, so this is what I've mentioned here. Basically, if k is greater than zero, so your x naught will be if x naught uh, basically here means that the value of x at point t equal to zero. So here what is happening is if both uh, if basically x naught is negative, dxdt will also have to be negative, because the product has to be positive, which is k. So if k is greater than zero, either both has to be negative or both has to be positive, which makes it unstable. It basically the x grows and dxdt grows as well. So there is no basically convergence. There is no bound solution for that equation. On the other hand, if k is less than zero, you have either you have one to be negative, one to be positive, and which basically makes it a bounded solution, where xf is equal to zero is stable. If this is harder for you to understand, just keep the maxima and minima analogy in mind. So basically, you have your dxdt equal to k. So if you differentiate it again, say for example, uh, you differentiate it again, you will get something of if you see k is greater than zero, so your system will be unstable because it will be a maxima, and if your k is less than zero, it will be a minima, because your k will determine the sign of the basically the curve. So if it is greater than zero, it will be kind of a maxima, and if it is less than zero, it will be kind of a minima. So the stable and unstable steady states are determined by the value of the k. So this is basically a basic concept in ordinary differential equations, and if you try to solve them. So yeah, this is kind of something you need to keep in your mind when you are solving, because you can just look at the equation and tell by the value of the parameter if the system will be stable or unstable. Now we'll look into different kind of ODs and different kind of like reactions and how you can form ODs from them. These are kind of fairly similar. So you have bimolecular reactions where two kinds of reactants are involved, giving a product with a reaction rate K. So basically your uh, rate of degradation of X dxdt will be dependent on uh, will be equal to minus kxy. So it will be dependent on basically how rate into basically how both of them are degrading, and same for your dy dt. In case of dz dt, it will be a positive because it is z is getting produced while xy are getting degraded. So these signs also you have to keep in mind while looking this differential equations, to like it will signify whether it is getting produced or whether it is getting degraded. So this is another example like that. But this is kind of a degradation. So z is getting degraded to x and y. So yeah, your dx dt will be dependent on z and the reaction rate. Same with dy dt, and your dz dt will basically depend on how it is degrading itself with the reaction. So uh, these are different kinds of Basically, one is basically a dimerization uh, you can imagine, and this is basically a degradation. And there's something called reversible dissociation as well, where the equation is basically reversible under certain conditions. So maybe uh, in the cell, maybe some proteins are coming together under certain pH and making a dimer or a complex protein with two or three proteins involved. And then when a pH or the temperature is changing inside the cell, it is getting degraded back to its original component. So this is kind of an example like that. So you have a forward rate of reaction, K plus, and also you have a reverse rate of reaction, which is a K minus. So your X will depend on both how sorry, X and Y are getting degraded, and also on how Z is getting formed. So this, sorry, yeah, sorry, I got confused. Yeah. So your dxdt will depend on how your xy is getting depleted and z is getting formed. Same with dy/dt, and your dz/dt will depend on how it is getting degraded and also on how xy is getting degraded to form z. So these things are basically very common. These kind of equations are very common when you are trying to depict chemical reactions, because maximum of the chemical reactions that we see in our cell are enzymatic and reactions and also reversible reactions. So basically, we'll see in the Michaelis-Menten equations of how we can use this. But yeah, this is how we basically generate ODs from basically using chemical kinetics and reaction rates and how and different kinds of reactions. So yeah, you can use certain constraints to basically reduce the number of equations. So we have had three equations here, as in the previous slide from this reversible dissociation. So we have these three equations, and using conservation laws, which is basically mass conservation, basically x plus y equal to z. These are like these kind of constraints you can have on the equations, not only while handling chemical kinetics equations, also when you are like say doing kind of seeing how a gene is getting formed or how a gene is forming an RNA which is getting degraded, this kind of stuff also there also the law of mass action holds. So basically conservation laws like these, they can help you reduce this kind of basically constraints. So if you just add the first and the last one, you get this equation, and if you add the second and the last one, you get this equation from where you can solve out x and z together from one and y and z together from another one, and then you can just put these values. Basically here will be xt plus zt will be, say, for example, here is this x naught plus z naught, which is given as a naught. So your xt will be a naught minus zt, and your yt will be similarly b naught minus zt, and you can just substitute these values here, and you can get a from a three differential equations, you reduce it to one, which is much easier to solve. So this kind of constraints you can have on different kind of chemical reactions from like these conservation laws, mass conservation, to get down your number of ODs. Basically, you already have a prior relationship known between, basically an algebraic equation known between the different components of that system. So if you know that from prior knowledge or basically uh, experimentation, you can use those techniques to basically reduce the number of ODs, which will help you solve it in lesser time and more efficient. Now, as I talked about at the beginning, these kind of equations we are seeing here are fairly simple, but when you're going to model like real systems and networks and signaling pathways, etc., these equations tend to become very complex. So, although these will be ordinary differential equations only, but not always will they be linear or basically fairly simple to solve analytically. So in 99.9% cases, you won't be able to solve the system of equations linear analytically. So there, what we do is we do numerical, we take the help of numerical methods. So we find numerical values which are y1, y2, y3, which correspond to a given numerical values of the independent variable, which are x1, x2, x3, and these ordered pairs x1 and y1, x2, y2, these should satisfy a particular solution. So these values should satisfy your original constraints and basically the initial conditions and all those things that you have put on the equation. And these you need to numerically find these values, and you can call these values states of these equations. So these are basically group you can like assume these to be different states of the particular compound or the particular network you are modeling, and these basically the solutions that give you will be various states that satisfy the ordinary differential equations that you have modeled. So and also like this will give you like a set of values. So it will give you a kind of a curve or a plane or something like that, and you have to you can see like trends from those kind of values or curves and straight lines and whatever you get the answer is. You can see what kind of states the particular network or the particular pathway is going through across different time points according to the equations you have used to model. So uh, this this type of solution is called a point-wise solution. uh, sup- Suppose you need to solve this dy dx equals to fxy with an initial condition yx naught is given as y naught. Now by the numerical solution of the differential equation, let uh, the yx naught equal to y naught comma yx1 comma yx2 be the solution of y at the different values of x, x0, x1, x2, etc. And your y equal to yx be the exact solution. And these truncation errors that result from using this approximation in place of an exact mathematical procedure, you calculate these errors and you try to minimize these errors. So one such method is Euler's method that we use for this numerical solution of ODEs. We can come we can use Taylor series as well. Taylor series is also one of the possibilities to use uh, for these kind of equations. So what we, in a series solution of y in terms of x, which will yield the value of y at any particular value of x by direct substitution in the series solution. Basically, you'll have x as a polynomial which is represented, and sorry, y will be represented as a polynomial of x in a series, in an infinite series, and you can just get the value of y by directly substituting x in the series and taking a sum. So these kind of methods are used in basically series solutions, and but in case of uh, in case of basically Euler method, it's a little bit specific, and the values of y at specified values of x will be taken. So basically, if you take the point x0, x0, x1, x0, x1, x2, etc., and the differences in these values you take as h, which is the step. So xi, x1 minus xi minus 1, basically this is xi, this is a misprint, xi minus x minus xi minus 1 is equal to h. So basically your xi will be x naught plus I into h. So your all the x values will basically come in a series. So it will be gradually incremented according to the h value. So and if you try to find the equation to the tangent to this curve, it will look something like this. So y minus y naught equal to this is basically the differential. This is the slope of the curve at x naught comma y naught and into x minus x naught. This is a equation of a straight line. This is your y coordinate. This is your slope. This is your x. So and if you simplify this, you get this value. Y1 will be equal to y naught plus h of y prime naught. So basically, you have y naught, and then you differentiate it, and then you put the value of y naught there and multiply it with h, and you add it with y naught, you get another solution. So these kind of you go on doing it iteratively. So you have y is differentiated, put the value of y naught multiplied by h plus y naught will give you y1. Similar with y2, and so on, etc., etc. And your h will be basically the difference between x1 and x0. This is known as Euler's algorithm. I have basically given you an overview of this algorithm. This is a little bit more sophisticated than this, and you can read about it a little bit more. And basically, engineering mathematics books quite describe this well. The Euler's method. You can take a look at it, and we'll not be using Euler's methods directly, but the point is, yeah, I just wanted you to know how these numerical methods work. There are other methods as well. There's one Range-Kutta method, which is a very popular method for solving numerical ODEs, where they use the fourth order Range-Kutta method to solve it. So I'll not go into that. So I just wanted to give you an example. Okay, so first we looked at how we can form ODs. Next we looked at how we can solve ODs. Now we look at how we estimate the parameters. Now, mathematical modeling is an essential tool in systems biology, and to ensure the accuracy of these mathematical models, these model parameters must be estimated using experimental data, a process called regression. And also, pre-regression and post-regression diagnostics must be employed to evaluate the model goodness of fit and the reliability of the estimated parameter values. So basically, how your model is basically how your solutions to the model is basically fitting a curve, fitting a particular trend is how you determine if your parameters are working well or not. So if it isn't working well, the parameters are not very good, it will not fit the experimental trend. So you need to design, you need to select your parameters very efficiently, and you need to evaluate how the goodness of fit, evaluate the model goodness of it, basically how your model is fitting the data. So and then you vary your parameters like that. And there are various methods of these parameter estimation. uh, the two most popular are maximum likelihood estimation, which we called MLE, and there is also least squares fitting. And these are the most common regression techniques, yielding parameter values and their variance covariance matrix. They work under the assumption that the estimated parameters have a normal distribution. This is something this assumption that the parameters have a normal distribution. This is something that is assumed all across estimation theory. If you look into it, so there, if you from a statistics point of view, the the signal, the noise associated with the signal. I'm talking in terms of signal processing because estimation theory is primarily used in signal processing, and we learn estimation theory through signal processing. So there is something called a signal and a noise. So the noise is always assumed to be normally distributed to get to see how to get the PDF of us of the signal. So basically, across many such techniques, you'll see that we are assuming that that the parameters, or example, the even the features are normally distributed. This is an assumption we make to mathematically aid us in basically solving the equations for the parameters, etc. Just a second. Yeah. Uh, uh, yeah. Uh, Sorry, just get distracted. Yeah. So these kind of assumptions we make to basically help us in aiding the calculation. And in certain cases, if you don't make these assumptions, that you assume that these are normally distributed. If you don't make that assumption, it gets very hard to solve stuff, and in many cases, you won't be able to solve stuff. So this is also a very like. very kind of common assumption that we make, that stuff are normally distributed. And this is actually, if you look in nature, it's kind of true. If you look at the distribution of height, etc., height, weight, not weight, but in case of height, it is very normally distributed. So there are, nature also shows normal distribution for a lot of stuff. So it's not it's not very foolish to assume that things might have normal distribution. So uh, they work under the assumption that the estimated parameters have a normal distribution, and this when this assumption is not valid, Bayesian inference might be used, yielding a full parameter distribution. Then you can like go through the hard way, yield the whole parameter. I mean, you need to know what kind of distribution it is. If it is Poisson, it will work in a different way. If it is a certain binomial, etc., it will work in a different way. But yeah, we assume it to be normal. And prior to the regression, the structural identifiability of the model must be assumed, assessed to determine whether model parameters can be uniquely determined and what data are required to achieve that. So basically, if your model is structurally identifiable, it the parameters must be uniquely determined. The parameters must be very specific, so that yeah, then only your model is structurally identifiable. And post regression diagnostic tests include testing the model's goodness of fit, meaning how it is fitting the curve, determining which model among competing ones fits the data best, evaluating parameter determinability, and evaluating parameter significance. And parameters in probabilistic models must be inferred either by indirect inference or by Bayesian methods. In indirect inference, model parameters are estimated by minimizing differences between intermediate statistics that characterize simulated and experimental data. This is kind of what we'll do. We'll estimate these parameters in an indirect using indirect inferences. Linear least squares and maximum likelihood estimation is are examples of that. Uh, we'll not use Bayesian methods here, but you can do it using Bayesian methods as well. But we'll look at how basically how the predicted values are differing from the experimental values, and we'll try to minimize that. So first comes the linear least square method. So the least square method is process of finding the best fitting curve or line of the best fit for a set of data points by reducing the sum of the squares of the offsets. Basically, if this b here is determining how it's basically the difference between your predicted and your experimental value. You take basically a square of that and you sum it over all points. So say for example, your points are like these distributed, like, and your curve and your basically model tells you the curve is like this. So how is it like how can you say if it is the best fit or not? So you make a cost function. In this case the cost function is sorry in this case the cost function is a linear least square. So you basically subtract your uh, experimental values from what it is predicted, take a square and basically add them up. So you get a sum of those least squares and you need to minimize that sum. So it's your cost function is the linear least square, a sum of the linear least square, and your idea is to minimize that cost function, and whatever values of the parameter minimizes that cost function the most, that will be the most efficient parameters for your model. So during the process of finding the relation between two variables, the trend of outcomes are estimated quantitatively, and this process is termed as regression analysis. The method of curve fitting is an approach to regressional analysis. This method of fitting equations, which approximates the curve to a given raw data, is the is the method of least squares. Uh, it is obvious that the fitting of curves for a particular data set are not always unique. That is, thus it is required to find a curve having minimal deviation from the measured data points. This is known as best fitting curve and is found by using the least squares method. And the least squares method explains the curve that fits the best is represented by the property, and the sum of all the squares of all the deviation from a given value must be minimal. This is basically your function of linear least squares. You sum it up across all your values and whatever parameter reduces this the cost function the most is the best efficient parameter for your particular model. Next comes maximum likelihood estimation. Okay, so maximum likelihood estimation for like performing maximum likelihood estimation, either you need to assume or you need to know what is the PDF of the basically the distribution of the of your values of your values of your parameters in this case. So you can assume it to be normal. You can have experimental proof that it is normal or any kind of other distribution, but you need to know what the PDF looks like. So uh, let x1, x2, x3, etc. be a random sample from a distribution with a parameter theta. And suppose that we have observed these x1 equal to small x1, x2 equal to small x2 up to xn. And if these are discrete, this is given by the PDF. And if it is continuous, it is given by the, it's basically the same. This is a discrete PDF. This is a continuous PDF. So basically this tells you how your basically distribution is looking. If this is a normal distribution, you replace it with the equation of the normal distribution. Now, in these cases, this is the idea is fairly simple. You have your PDF, and you want to see the maximum. You want to find the maximum value. So basically, you have the PDF. In most cases, it will be exponential. So what generally they do is they take a log and then they differentiate it and make it zero, and find the parameter for which uh, that whole function is basically the dx dt, the derivative is zero for that function. So it's a fairly simple concept. You have a PDF, you take a log, that's a log likelihood. The PDF is your likelihood function. The if you take the log of that, that's a log likelihood function, and whatever value maximum, whatever value of theta maximizes, theta is your parameter here. Whatever value of theta maximizes your likelihood function is your best fit parameter. So here it is given. This is for a discrete case. So your theta ml will be this one, which maximizes the PDF. This is basically your distribution. In this case, this is discrete. This is continuous. But with your idea is the maximum likelihood estimate of theta will maximize the PDF at that value of theta. So in this case, it will be here. For this case, it will be here. So uh, he- here also, if you read it, it will say the same thing. It's basically that now they have defined likelihood function, and you're ready to define maximum likelihood function. Let x1, x2, x3 be random samples from a distribution with parameter theta. The maximum likelihood estimate of theta ml is the value of theta that maximizes this function. So how do you find the maximize value of theta for this function? Just a second, guys. Can you hear me? My earphone went off. Hello.
Yeah, yeah, yeah. We can hear you.
Okay, okay. Sorry. Okay. Yeah. So basically, you have this is your likelihood function. Your likelihood function is basically your PDF. Whatever distribution you observe, whatever value of theta maximizes that function, maximizes your PDF is the your maximum likelihood estimate of that parameter theta. So yeah, so we saw two methods using for parameter detection, parameter estimation. There are much more methods that are involved. You come across linear unbiased estimators, which are known as basically BLUs, and there are other kind of estimators as well. There are a lot of estimators in estimation theory. You can like if you're interested, you can go through a book. There is a book on estimation theory. I don't remember the name exactly. I'll send it to you after class if I remember. So it's a basically it's a signal processing book where they explain how we can derive these kind of these kind of equations. So we are assuming that this parameter is maximizing the the PDF by just differentiating and finding the parameter at that where dxt equal to 0. But the concepts and the rationale used for these are basically explained in a proper estimation theory course. So if you want, you can take a look at that. It is quite interesting. Okay. So coming to our basically parameter estimation problems, what kind of estimation problems we have in the context of systems biology. So non-linear dynamic systems, as in systems biology, are usually modeled as a non-linear programming problem with a differential algebraic constants in mathematic models. So you'll have a differential equation something like this, and you'll also have algebraic constants. So your initial conditions or how the reaction rate is varying or something like these. You'll have a set of algebraic equations, you'll have a set of differential equations. The algebraic equations will give you constraints to the differential equations. And to model these nonlinear dynamic systems, uh, this is the form of equations you will find. So your it will be a function of a lot of parameters. So these parameters are described here. So your P will be a vector of control parameters for the differential algebraic equations, which need to be estimated. So it is kind of a matrix or a vector of the control parameters. X will be the differential state variables, the variable that will describe the different states of the particular system, and V will be a vector of the other parameters, which are usually obtained through experimental studies and basically which will remain constant throughout your model, and will not be needed to be estimated because you already know what those values are. And also there will be uh, possible equality and inequality constraints like H and G. So you can have certain like constraints to the equations at particular points, saying ki, like it will always say at this point the value will be zero, or at this point the value will be this much, or below this point the values should be negative. These kind of constraints there will be there. And also you'll have P, which basically which is a parameter which will be bounded by unequality constants. This basically it will be within a range. So these all kinds of parameters you can have in systems biology models, which are non-linear, and these become hard to solve, as I said, analytically. So these need to be solved numerically with the help of these constraints. Obviously, then the solutions need to satisfy these constraints. So yeah. Next, we come to a very important model, which is the Michaelis-Menten model. So this model takes the form of an equation describing the rate of enzymatic reactions, and it relates a reaction rate to the concentration of the substrate. The enzymatic reaction in this model involves reversible reaction where an enzyme binds to a substrate S to form this enzyme substrate constant, which this part is reversible, but the enzyme substrate constant breaks into the enzyme and the product. It gives back the enzyme and the product. Uh, and this part is irreversible. So you have two parts to this equation. So one is a reversible part, the combination and the breakdown of enzyme substrate complexes, and the reversible part is getting the product and the enzyme back from the enzyme substrate constant. So by applying law of mass action, it states that any chemical reaction is directly proportional to the product of the masses or the concentrations of the reacting substances. The system of differential or four ODEs basically uh, are formed, which describe the rate of change of the reactants over time. So you have four basically elements here: E, S, S, and P. So you can model each of these elements differently. So as a differential equation. So your dEdt, it will be basically uh, minus of kf into es, basically how E is getting degraded with with the forward reaction, and also how E is getting reformed with the backward reaction. So minus kf into E into S, and also k reversible of es. So basically this is from here also E is coming back, and also this ES is also getting giving rise to giving back enzyme with the product. So this rate is known as kcat. This is the catalyzation rate. So this is also added to this OD. Similarly for S also, you can see this is fairly simple. So S, it is getting degraded with for the forward rate and getting replenished with the backward rate. ES on the other hand is getting uh, formed from the getting formed from the degradation of E and S, and also this ES is also going and making E and P, so that is basically coming as negative. And for the last part, the product is basically dependent on the concentration of the ES complex. So these four ODs you can make from this equation. And in the original analysis, Michaelis and Menten assumed that the substrate is in instantaneous chemical equilibrium with the enzyme substrate complex. And an alternative to this analysis was proposed 10 years later by Briggs and Haldane, and which is the known as the quasi-steady state of the system. This is something, this is one assumption also you'll find made quite frequently across the systems biology models, that either the system is quasi-steady state, either the system is showing quasi-steady state or not, etc. This kind of constraints will be put on ODs when we're trying to solve those ODs. So this is something we'll see quite frequently across different systems, particularly in systems biology. Uh, I- Basically, it assumes that the concentration of the intermediate complex is approximately steady throughout the progression of the reaction. And both approximations assume irreversible dissociation of ES complex to product and the free enzyme that yields the following equation of the velocity of the reaction. So your dp/dt will be the velocity of the reaction. If you can solve it analytically from here, it will give you something like this, which is Vmax, which will be the product of the initial concentration of the enzyme into kcat into S, which is the substrate concentration by Km plus S. And this Vmax is basically denoting the maximum velocity of of the the reaction. E will be the initial concentration, as I said, and Kcat is the catalytic rate constant, and Km here is the Michaelis constant. And the S naught, you can add S naught, the initial value, if it is known. We generally assume it is known, so we can add that as well. And one thing to just keep in mind, these uh, basically the Km and basically what this equation does is, Michaelis Menten, it gives a steady state. It gives a saturating behavior, which is very different from the initial reaction that we assumed here. So this does not give a steady, not this. This equation does not give a steady state. It is either increasing or decreasing. But if by the Michaelis Menten, the difference here is it will give you a saturating steady state. And also one thing to keep in mind, here I talked about this quasi-steady state of the system. This here it is assuming that the concentration of the intermediate complex is approximately steady during the whole reaction. One other way to look at it is it attains that equilibrium very fast, so that the uh, the concentration is unchanged over the whole of the reaction. So another way to interpret it is that the equilibrium is attaining very fast. So that also is an assumption that we'll use in future models. So something to keep in mind. Okay. Now, this model provides crucial information about the nature of the enzyme in the form of the kinetic parameters. The Michaelis constant, which is the Km, is the concentration of the substrate at which the reaction rate is half the maximum rate. I think you guys all know this. This is a very simple thing, and like all of us have studied that the Vmax is the saturating point, and half of the Vmax gives the Km. This is an inverse measure of the substrate's affinity for the enzyme. The smaller the value of km, higher is the affinity, hence the rate will approach maximum velocity with a lower s than other reactions with a lower km. So if your km is high, your that means your affinity is high. That means it will reach that saturation point much faster than other reactions with lower km. And so the catalytic rate shows how fast the reaction is. The kcat by km constant provides the knowledge of how efficiently an enzyme is converting substrate into a product, and the curve describing the relationship between the velocity and the substrate concentration in the Michaelis Menten kinetics can be formed as a nonlinear regression model. The commonly used model described use express model is expressed using the exponential function. So this is how basically the model is described. V equal to the velocity will equal to Vmax into 1 minus exponential of minus E. B is a parameter, basically exponential of minus S. And you can just what to say, like you can expand this using the Taylor or the Maclaurin series. If it is infinite, you can take a Maclaurin series. Here it is one. Since it's one, you can take a Maclaurin series here, and you can expand it something like this, with where this a1, a2, up to ak, these will be different parameters, basically different values, constants that you'll use in the model. So from this you come to this. So this is basically how the regression is done by expressing it as an exponential model. Okay. One what to say, one extension of this model can be applied in the case of competitive inhibition. Now, what is competitive inhibition? It is basically when a second substrate can bind to the enzyme and which can prevent the primary substrate from doing so. So basically, this concept is well used in during drug targeting. So if you have an interaction, a particular signaling molecule, say, is coming and binding to a receptor, and it is activating a signaling pathway which is faulty and which is causing disease. Now, if you want to stop that signaling pathway, what you can do is you can design a drug target which exactly fits into the that receptor, just like how the original signaling molecule would. But if that the other the drug fits in the receptor, it will not perform the signaling. So this can be used as a competitive inhibitor. So uh, as I said, this is, for example, a mechanics describing the action of a drug on a receptor protein on the cell surface that would interact with the external world. So you have an enzyme here. This is a competitive inhibitor which basically takes up the place of the substrate, and it does not allow the substrate to bind to the enzyme to be converted to the product. So the chemical kinetic model will look something like this. Here, uh, I is the inhibitor here. So your chemical kinetic model would look something like this. Uh, I'm audible, right? Yeah. Sorry, guys, my earphone is not working properly today. I'm audible, right?
Yeah, 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 yeah,
Yeah.
yeah.
Okay. Yeah. So your basically your set of reactions would look something like this. So this is your I can interact with the enzyme and give you a complex, or your S can interact with the enzyme and give you a complex. This is the Michaelis-Menten equation that we just saw. The substrate and enzyme giving a complex, which is basically reversible, and then the complex is basically breaking down and giving into the product and the enzymes. In this case, just another equation has been added where the inhibitor also can bind to the enzyme irreversibly and give another complex. The set of ODEs describing them will be quite long, so there will be a few parameters involved. So how many elements do we have here? We have S, E, we have C, E. So here we have 4, and then we have I, 5, and C2, 6. Well, 6 equations we'll have here. So you can see we have six differential equations here. So S, E, C1, C2, I, and P. So it's like the equations, writing the equations is fairly simple. You see how from where that particular element is getting produced or degraded according to the rate, it is proportional to that. So just write the equations. And now you'll have conservation loss. So your initial uh, enzyme concentration, your E naught, will be the sum of your concentration of the complex 1, complex 2, and the free enzyme. So this will be one of your conservation laws. The other conservation law will be your initial inhibitor concentration will be the free inhibitor plus the inhibitor in the complex 2. So these after these applying this concentration conservation laws, you can reduce the number of differential equations here. Then you apply quasi steady state approximation where you assume that the C1 and C2 does not change throughout the reaction. So it is in equilibrium and it attains equilibrium very fast at the initial only, and it stays like that throughout the whole equation, whole reaction. So from there, these theta are different parameters for the different elements, and from there you can just you can solve it using the values of these parameters, and you can get the product formation rate like this, which where your Vm is your basically the maximum rate, and you get something like this. We'll come to this equation in a little bit when we study Hill function. So, yeah, next comes the concept of cooperativity. What is cooperativity? Cooperativity is when n molecules of a substrate must fit together with the enzyme in order for the reaction to take place. So there are various components, various substrates, and all the substrates have to come and fit to the enzyme to give the reaction. So examples can be ligand binding to the cell receptors or binding of transcription factors to DNA to control gene expression. This is something that we are very interested in, the binding of transcription factors to DNA to control gene expression. This is something you can apply in the case of gene regulatory networks or transcription regulatory networks. So the concept of cooperativity becomes very important. So how does the kinetics work? So you have uh, substrate, n molecules of substrate, and an enzyme which giving you a complex which breaks down into your product and enzyme. So all the n of those substrates has to come and bind to the enzyme to give you the product. So similarly, you can write the ODs for these equations. And after this quasi steady state approximation, you get something called for the product formation, the rate of product formation, you get an equation like this: Vm into s to the power n by theta plus s to the power n. The theta is your parameter. Now, if you make yeah, just a second, guys. I just put this here. Okay, and so still audible, right? Yeah. So yeah, so if you just modify this theta to the theta n to theta to the power n, this is what gives us the Hill function, which is uh, s to the power n by theta to the power n plus s to the power n into Vmax. So it is written like this: h plus and minus. We'll talk about what these are. H plus of s theta and n. These are the three parameters of this function. Where s is your concentration of S is the concentration of the substrate, theta is the parameter, and theta is basically the constant parameter, and n will be the number of substrate involved here. So this form of this form of an equation, form of the equation is called an Hill function. We'll look into Hill function a little bit more. So you can have couple of type of responses from these if you solve these Hill functions, and you can uh, either have sigmoidal functions or hyperbolic functions. First, let's talk about sigmoidal So this kind of responses are very, if you look into experimental data, this kind of responses are very common for saturated growth rate and saturated decay rate. So this basically will be your growth rate. This will be your decay rate. So the growth rate, if you look carefully, look something like the microbial kinetics, how a microbe grows and reaches saturation and then dies off. So the like the if you look into the growth of E. coli, it will look something like this. This is known what is known as a sigmoidal function. So if it is positive growth, your Hill function will be basically h to the power n by theta n plus h to the power n. If it is negative growth, you just put a 1 minus to this, and you're basically Sn cancels off, and in your numerator you're left with theta n. So the positive for the positive growth, it is this h plus function, and for the negative growth, it's this h minus function. And what is theta here? The theta will be the threshold. What is the threshold? The value of S at which H plus minus reaches half of the saturation value. So this theta will determine uh, what is the half of this. You can imagine it to be kind of an analogy for Kn. So if this is the Vmax, half of the half of the rate of that will correspond to the theta. So uh, this is what uh, the Hill function denotes, and n is known as the Hill parameter. So like changing n will change the responses. We'll see how here. So if you're, say, for example, from the previous example, you saw dpdt equal to vm into s to the power n by theta n plus s to the power n again. Now for n equal to 1, if you put n equal to 1 and solve it, the the dpdt versus s curve will look some like a hyperbolic curve, like this one, second curve. Now, if you increase the value of n, which is to greater than 1, it will move into a more of a sigmoidal curve. So the value of n determines how your how your response will look like. Will it look like a hyperbolic, or will it look like a sigmoidal? Now, what is the difference? For n equal to 1, the graph is concave. So I hope everyone knows what concave is. So for n equal to 1, the graph is concave. And when you're increasing it more than 1, this concavity, it, it moves towards more concave from both the side of this half value. So this will be pushed here and this will be pushed down. So you have this graph. The graph starts with concavity up and finishes with concavity down, and you have different stability properties. What is the effect of this? So if your curve becomes more sigmoidal, it means basically your n value is increasing. So if your n is 1, it will give you a hyperbolic, and if you uh, slowly increasing it more than 1, it will take the sigmoidal shape. And what it signifies is, when it takes the sigmoidal shape, it basically increases the sharpness. So if n grows even a little bit, the states jump from one into another. So say for this point, if it is 2 sigmoid, so if n increases slightly from, just a second, yeah, if n increase let's see, huh, if n uh, moves from just from here to here, there is a great shift in the state. So this tends to act like a Boolean switch. So it's kind of a switch. It's an all or nothing behavior. Either it is on or it is off. If your n is on the lower side, if n is closer to 1, it will not be like that. It will not be like an on or an off state. It will be more like a transition from from one state to another, for very gradual transition. But in this case, in case of sigmoidal curves, it will be a straight jump from one state to another, which can be termed as the ultra sensitive response, which is the all or nothing behavior. So yeah, now we come to the concept of multi-stability. Now consider the enzymatic reaction in the quasi-steady state approximation. This is the equation that we already looked at. It's safe here n is greater than equal to 1. Now assume this is an autocatalytic process. So basically P will enhance its own concentration. So P is the product here. So it basically giving a kind of a positive feedback. So P is enhancing its own concentration. So S will be proportional to P. So S equal to alpha P. And if you add a degradation rate, meaning the product, uh, the rate at which the product is being used or naturally degrades or diffuses, etc. There's a degradation rate associated with the product with a rate of gamma. So the equation will look something like this. You just in place of S, you put in alpha p, and you add a degradation factor of minus gamma p. And if you assume all this to be equal to 1, your equation becomes more simple and it looks something like this: p to the power n by theta n plus p to the power n minus p. Now, what are the possible steady states for this? So, what it means is for which values of p dpdt equal to 0. First is an hyperbolic case. If you solve this, there are two cases you will find. One is a hyperbolic case where basically A will be the unstable equilibrium point. So A is here. So this is the hyperbolic production rate. So A will be a unstable equilibrium point, and B will be a stable equilibrium point. So basically where the degradation rate and the product rate curves are meeting each other. So there are 2 points for that. So basically it is showing that it is in stable state, steady state. So one will be a stable steady state, which is the B1, and one will be an unstable steady state, which is the A1. So the P value will converge uniquely to an intermediate value in case of the hyperbolic case. So it is converging to an intermediate value. In case of a sigmoidal case, the case is a little bit different. So your A will be, you'll have more of these steady states. So your A will be an here at the initial, it will be it will be a stable equilibrium point. Your B here will be an unstable equilibrium point, this point. Your C here will be a stable equilibrium point. So you'll get three steady states instead of two. And this, the value of P will convert to either C or A, whichever it is. So from here you can go to either A or C. And this value will converge to A or C depending on the initial conditions. And this is what is known as bistability. You have multiple, you have two steady states from which a point can converge to. So you can have like this, you can have multi-stable states as well. This is an example of bistability. You can have tri-stable or tetrastable states as well. Tri-stable state is a very common tri-stable state that actually I worked on is there's these T cells that we have. So there's from the progenitor cells, the T cells uh, diverge into TH, various helper cells. So from TH0, that the progenitor is known as. So you have TH1, TH2, and TH17. Three kind of states you find in three kind of differentiations you find in T helper cells. Now these three states, TH1, TH2, and TH17, these three states of T cell are in basically a network within their cell where they inhibit each other and upregulate each other. They kind of act as basically toggle switches. So you have, you are inhibiting your partners and activating yourself. So these kind of states, and if you model that state, that was a tri-stable, that's a triangular curve. You'll have three nodes and six edges between them. And if you model that system, you'll find there are bistable states existing between any two states of the T cell. So TH1 and TH17 will have an intermediate state, which is neither TH1 nor TH17, but having properties of both of those, and it will be in a stable state. So finding bistability or multistability is important in those cases, those applications where Like if you see there's a differentiation or a transition from one state to another, there may be a possibility then within that transition there exists a state which is stable and which is neither of those endpoint states. So those kind of states you can find with the help of these bistability or tetrastability equations, if there exists. So yeah, now we'll come to some examples. First is the concept of feedback regulation. So as I said, as the previous example also showed, P, the concentration of P modifies the concept, basically dp/dt. P regulates itself. If P enhances itself, it will be known as the positive regulation. An example of positive feedback will be gene regulation. So here one example is given. So you have a gene which is making an mRNA at the rate of k1, which is forming a protein at the rate of k2. Now this protein is going and enhancing the transcription of this gene. So this is which what is known as a positive feedback. So here your variables will be x1 will be your mRNA, x2 will be your protein, and k1 k2 will be here the production rates, and gamma 1 gamma 2 is the degradation rate. Now if you assume like the rate of change of x1, the rate of change of mRNA, and the rate of change of protein. So this is basically this will follow a Hill function from gene to mRNA with the parameters of x to theta and n, and it'll also have a degradation factor of gamma x1, the gamma 1 x1 that we are showing. Similar is the case for dx to dt. Here, it'll only depend on the concentration of x1, and uh, it'll also have a degradation rate of gamma 2 x2. Now, if instead of the protein that is enhancing itself, if it is inhibiting itself, then we have what is known as a negative feedback. Here, the signs are slightly different, but the equations look very same. So this was basically formation, Hill function formation, and this is basically Hill function of degradation. So that's the only change here. Rest of it is more or less the same. And modeling these ODEs, you can get these steady states. So in this case, this is basically a single steady state. Here you can have, we are seeing here multiple steady states, and like you can have whatever. These are like just examples. You can have various steady states, or even you can have no steady states at all. So that is also possible. So this is just an example to show to how to calculate these feedback regulations and all. And yeah, now we'll look into a little bit more comprehensively into a gene regulatory network. So assume this gene regulatory network. So you have a gene A and a gene B. So gene A is producing mRNA, which is producing protein A, which is inhibiting gene B. Similarly, gene B is producing mRNA B, which is producing the protein B. But this protein is just a second. Yeah. Hello. Yeah. I'm audible, right?
Yeah, yeah, yeah.
So my earphones have no charge. Okay. Yeah. Yeah, this is a simple gene regulatory network that is shown. This protein A is inhibiting gene B, and this protein B is inhibiting gene A. So how do you write this ODs for this? So just assuming basically, yeah, your DXXGA and your DXGB. These are basically the rate of formation of the gene products. This can be labeled as this can be modeled using the Hill function. So in this case for gene A, this is getting upregulated only. So this will continue keep on forming. So it'll be the positive Hill function, the H plus, and in case of gene B, it'll get degraded. Basically, it'll not be forming; it'll degrade. So it'll move in the opposite direction, and hence the H negative function. And we also have a degradation, basically the formation of the products which aids in this degradation process as well. We have those factors as gamma, with gamma parameters. So this is the simple ODE for these two gene regulation, these regulations. Now you can add levels of complexities to these regulations. Say for example, you added a delayed regulation complexity to this whole thing. So basically you add two time delays, this tau 1 and tau 2, basically saying okay, like immediately after the product is formed, it'll take some tau 1 time to get to the protein, and after the protein is formed, it will take some tau 2 time to get to the gene, so to influence the gene. So these also you can model. So here see, in place of x, here the protein concentrations were taken, the xp's, and all. In this case it is transformed into basically this tau value, which is giving you the concentration of the protein at the particular time point. So basically, after tau seconds or tau minutes, the protein has been formed. Then the protein is eligible to influence the gene, or the regulatory mechanism. That also you can model. I'm not going into the details. This is a little bit complex, so I'll not go much into the details. I'll just show you what you can do with these equations. So yeah, you can add this time delay, and you can just substitute that in this equation, uh, in these equations, and you can get an OD. You can add indirect regulations as well. So you can add, say for example, your gene is forming an mRNA, which is forming an enzyme, which is catalyzing this process of the substrate to metabolite concentration. And this metabolite, say for example, is getting integrated into a repressors, which was basically inactive earlier. Now with the help of this metabolite, this repressor is active, which then represses this gene. So this is kind of a more complicated process that is going on. So these also you can uh, very not very easily, but you can, with the help of these parameters and ODs, you can model this. So you'll have your enzyme, your metabolite, and your gene. Three things you need to model together. So here the level of complexities increase. So now let's look at an example of a positive feedback. So this is taken from this paper from 2003. This is if you're interested in knowing in more great detail on how the different modeling is done, it is given in the paper. You can take a look there. So this is an example of a positive feedback. So gene for the lambda repressor, this is the CI857, and it's three upstream promoters. These are the three upstream promoters here. Were introduced in E. coli, and the lambda repressor is temperature sensitive. So changing the temperature will change the time at which the steady state is reached. And what are the conditions? So first condition is, if at most a single repressor binds, it will have a low steady state. So uh, these are the three points at which the repressors can bind. So OR1, OR2, and OR3. So if it binds only at OR1, the reaction rate will be slow. Next is, if the repressor protein also binds at OR2, it will amplify the reaction. So if both OR2 and OR1 are occupied, you'll have the maximum reaction. Now, if again and what again again the repressor is basically bound at OR3, then the whole transcription of this gene will stop. Now this OR, the binding of the OR and the repressor, this repressor is getting from this gene only. This is what is interesting. So basically, this gene is manufacturing the transcription factor, which is regulating itself. So this is kind of a positive feedback. So positive feedback in case of the OR2, at least till OR2. If it comes till OR3, then it becomes a negative feedback. So it's kind of oscillating between positive and negative. And just keep this in mind, ki like it is binding as a dimer, not a single uh, lambda. So there are two lambdas that are binding at a particular site. So uh, during basically modeling these equations, we are going to need that information. And it is giving rise to basically these states. We'll talk about these, basically how it is getting through the equations, but it is giving monostable high states. This coming back, this is basically an unstable state. And then you'll have monostable low states. Also in between you have, you'll have basically multiple steady states. So that is derived from these equations only. So what are your variables here? X will be a repressor, basically the product of this gene. X2 will be the repressor dimer, which can go and bind to the promoter. And your D, these are various D0, D1, D2, D3. These are DNA promoter sites with I dimers bound. Now, they're like basically separated the equations by either if they're fast equations or they're slow equations. What the basically the fast equations are, why they have done that. For the fast equation, basically they are assuming the steady state is reached very fast. Basically the concept of quasi steady state assumption. So there they assume that the concentration of the intermediate is remaining same throughout the whole process, which is implying it is reaching the steady state very fast. Uh, Here, basically, they have divided those equations into these these set of equations which will reach steady state very fast, and the other set of equations which will not. So these are those. So the dimerization is basically considered, also the binding of these DNA sites with the dimers. These also have been considered. And now you see the slow irreversible reactions, which will be the transcription and the protein degradation. So the transcription and protein degradation will be irreversible state, and this will be slow reactions. And uh, this alpha value they have considered. Yeah, this alpha value they have considered, which is the basically the enhancement factor for this D2 transcription. Basically, your D2 is the third site. This the third OR3 site is basically D2, and no, sorry. Okay. No, sorry. The D2 is basically the condition at which both OR1 and OR2 is occupied, meaning the second state, which will be the fastest. So alpha will be the enhancement factor, that amplification factor for the gene to make it, the gene transcription to make it the fastest. And uh, you can basically put all these equations together in the form of these. If you consider Z to be the concentration of all the total all DNA, the transcription factors, the dimers, etc. If you consider all of the concentration as Z, then you can model this Z using using ODEs, dz dt. It will come like this. Will beta and your tau, your gamma will be basically the parameters, and the tau will be the change will be the delay in 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 like in the gene products influencing the transcription. And you apply these conservation laws. So you basically your all the DNA will be constant if you assume that, and you do some parameter shuffling. This is some complex mathematics I have not included here, and you can get the value of this d naught. So from these uh, four variables, you can eliminate one variable, and then you can put it here. And from d naught also you will get d1. So you can put it here, and your ultimate ODE will look something like this. Dz dt will look something like this. Is a very bad equation. It's looking like. So this is what I was talking about. This is a real world example of the of how ODE, how using ODE you can model a system. Now, this ODE you cannot solve using analytical solutions. This ODE you have to solve using numerical solutions. So this is what I was talking about. Now, from that, from Z, you need to separate out X, the value of basically the lambda concentration and the protein concentration from there. So you can separate out, and you'll get something of function of like this. So it'll give you, and if you put different values of it, it'll give you monostable and bistable states. See, the monostable has a this is basically showing the stability the of the state. So higher the number, more is the stable. So red, the more the red, the most stable. So here you can see these two red dots here. Here also two red dots. These will be bistable states. This will be monostable states. So you have a model that predicts that there will be some monostable high states, there will be some monostable low states, and there will be also some bistable states. So that is given in this curve here. Like this is an example of how this is an example of a positive feedback loop and how you can model these kind of loops, and you can get if there are monostable, bistable, or any other kind of stability present. Now, this is the last example that I have. I'll not go into much detail of this example, but this is a real world example I want to give. So, this is modeling of yeast cell cycle. This has been studied in very detail, how yeast cell cycle is regulated and all. Uh, they have been studying yeast for a very long time, so a lot of it is known. So, how do you build a model for this? So first you have a wiring diagram. So basically the pathways, the gene products connecting itself, the transcription factors, how they are regulating each other and all those stuff together. You have this wiring diagram. Then you make mathematical equations, basically make ODs from these, and then assign values to these parameters, just like we saw. So this is the wiring diagram, which is the basically the regulatory process describing all the all the regulations between different genes and transcription factors, and you have a list of ODs. This is a very small. I'm sure you can't see here, but this model has 36 ODs. They are mostly nonlinear. They have quadratic equations as well. They have Michaelis-Menten equations as well. Goldie-Forsberg, Goldberg-Quotient functions as well, and also these 24 algebraic equations, which tells about the constraints of these parameter of the differential equations. We have around 130 parameters, so it's quite a fairly complex system. Now, when you simulate this system using these differential equations that is given here, you what you see is it fits the cell cycle of the wild type. So your model is describing the wild type behavior of the cell cycle quite well. It correctly predicts the phenotype behavior of 120 of the 131 studied mutants. So that is a very big claim. So if you can model mutations and you can correctly predict out of 131, 120 mutants correctly, so it's a big deal. It means your model is very robust and uh, that means your model is very robust and is basically not sensitive to the values of the chosen parameters. So this is whole of the things that I wanted to discuss. So we started with how to get ODs, then we saw how to solve ODs, then we saw how to estimate those parameters for the ODs, and then we saw some examples, real world examples of how to solve these, how to make these models and solve for these states, and how you can make inferences out of these models. So this was the whole lecture today. I have one question you can try. So this is a very straightforward question. Uh, this is basically you need to calculate the linear least squares. So these kind of questions you'll get in your assignment. So you can try solving this. So yeah, just to tell you this, Jay, like you won't the things I taught were quite complex. So these kind of OD solving and everything, you won't be able, you won't be asked to do in your assignments. Your assignments will be much more simpler problems like this. But yeah, that is, I just wanted to give you how it actually works in the real world. So yeah, you can try solving this. Can put the answer in the chat. Yeah, that is correct. Can you tell me the LSE values for both?
Yeah, so for parameter 1, it's 5.5, and parameter 2, it's 4.71.
Yeah, it will come around 4.5. Yeah, that's correct. Okay. Here's one MSQ, multiple correct and uh, multiple correct question. So yeah, try this. Answers it. 1 and 4. Okay. Yeah, that is correct. So this brings us to the end of this session. Uh, if you guys have any questions, you can ask me now, or we'll close this session.
It was a lot of information, so I guess for me at least it takes a bit of time to process it, and then I I think it will be better if I mail you or something, if that's okay.
Yeah, I can understand this. This will be a little bit difficult because a lot of mathematics, ODE, and stuff are involved. So yeah, you can take your time. It's a little bit complicated, I understand. And if you do not have much background in ODEs and
Mm.
solving these stuff, I'll suggest there's a professor called Gilbert Strang from MIT.
Mm.
He's basically a pioneer in ODEs and um, basically linear algebra. So he has a lot of videos of MIT OCW on YouTube. You can check
Okay.
him out. He's a legendary prof, and
Okay.
he teaches very well. So if you have any problems regarding ODEs and stuff, you can watch like videos like those, or uh, you can read basically if you want to know more on a superficial level. Any engineering mathematics book is perfect for that.
Yeah.
So all these methods of numerical methods, say analytical methods, solving of ODs, all that is correct. So yeah, take your time, and if
Yeah.
you have any problems, yeah, let me know.
Because for me, like because after attending the lab sessions of week 5 and things like that, so
Hmm.
always when I'm seeing a problem, like when I'm looking at a problem, there's this two sets of things that comes in. One is the theoretically like understanding like what are the equations at play, and then how do we sort of like what equations are involved here, how do we sort of like come like arriving at the ODs and things like that. And
Hmm.
at the same time, there's a second sort of thought process which goes into how to sort of code it or something like that. Like where, like,
Okay.
how
Okay.
do I like, use this information? Then like, how do I sort of
Okay.
like code these? Like, do I manually like enter these values? Because in the last example, the cell cycle example,
Hmm.
considering the amount of equation things like that, how do we sort of go about uh, like modeling it essentially?
Okay. So yeah,
Mm.
for these kind of stuff, that these very complex equations that we have, so we have a meaning, like obviously we use programs like MATLAB and stuff to do it. Obviously we
Yeah.
cannot do it by hand. The point is, uh, yeah, you need to because your solving is particularly dependent on your on softwares like this. You need to know how to code for
Mm.
these equations, and how to do that on softwares like MATLAB. But the point is, for a general understanding of these ODs, not the solving part. Solving is much more mechanistic in nature. The creating
Yeah.
of these ODs will be the more difficult part, because
Yeah.
you give this input
Yeah.
to
Yeah.
MATLAB and will solve it. Yeah. So uh, one advice I can give is like start from very basic chemical kinetics. If you
Yeah.
understand chemical kinetics and how production and degradation works, and how you can like just small equations, how you can use how you can use differential equations to write to small changes, small equations and small kinetics, then I think if you have that base very well, any kind of equation you'll be able to interpret. So
Yeah.
chemical kinetic, in case of our cases, in systems biology related cases, chemical kinetics, understanding chemical kinetics is the most important thing. So every function, this wheel function and everything, these are all
Yeah.
based on chemical kinetics. So
Mm.
basic chemical kinetics, basic first order, second order equations, how you model them, normal, like how can you model a first order differential equation, that
Mm.
dx dt equal to kx, from where it is coming
Yeah.
from. So those fundamental questions, if fundamental concepts, if it is clear to you, I think it will help you a lot to understand complex systems, because like a lot of variables will be involved, those positive negative symbols, one will be degrading, one will be forming, one will be forming a dimer, stuff like this. So those information, those those information, I think you can, like if you know it on a much lower level, it'll help you understand there. But in general, yeah, I can understand it's a difficult topic, but yeah, okay, yeah, what can we do?
No, but it's very interesting. I mean, like this is something that sort of like it's more or less fun in the sense you sort of try to figure out what all
Hmm,
is at play, and then you try to like basically quantify them in a way,
hmm, hmm,
essentially, which is very fun. Like, and your the examples were really nice. I mean, to understand how complex systems could be, and then how like upon like increasing complexity, like how sort of the system like how big the systems essentially become
hmm, 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 hmm.
in a way.
Yeah, yeah, it is interesting. It is interesting, but yeah, it is at the same time too many equations involved, so it becomes a little more complex.
Yeah, thanks.
Yeah. Thank you. Then I'll close the session. We'll
Yeah,
meet next week, same time.
okay, sure. Yeah.
Thank you.